Now we're going to cover two important performance concepts: relative performance and Amdahls Law. Relative performance is useful to compare the performance of machines. So if I have two machines and I want to see how much faster one is than the other, I can use relative performance. I can also find this useful as an architect to determine the performance benefit or loss of adding or subtracting a feature. So I may have some great idea and I want to put it into my smartphone chip, and I need to know what's the benefit of doing that. Now, you might ask, why might I want to know the loss of subtracting a feature? Why might I take out a feature? Well, it turns out that if I can make my chip smaller, then I can reduce cost. So sometimes architects at the end of a project find that the chip is too big, and they need to take features out in order to meet the cost target. So sometimes you have to look at what's the cost, the loss of performance, if I take out a feature. And I can use relative performance to measure that as well. Here's the equation for relative performance, where x and y could be two different machines, or for example, x could be an enhanced version of machine y. Performance x over performance y is the inverse ratio of their execution times. Now, if x is an enhanced version of y, then it will have a smaller execution time, and this ratio should be greater than 1. So I get some kind of speed up and a performance improvement. The second performance concept is Amdahls Law. Amdahls Law tells us how much improvement I get with some sort of enhancement. And what it says is that the improvement that I get, the improvement that's possible with some enhancement, is limited by the amount of time that the enhancement is used. So here's the equation for Amdahls Law. Execution time enhanced, this is with my enhancement, equals the execution time affected by the enhancement over the amount of improvement plus the execution time that's unaffected. So what this tells us, if I have this great improvement idea, but it only affects a small number of instructions. So for example, let's say I have an enhancement to a square root. I have this great idea for a square root. Well, we don't use square root perhaps too much in our programs, so we expect to have a very small improvement in execution time. Let's take an example of a multiply. Let's say that a feature improves a multiply operation by a factor of 10, and that the total execution time of my program is 100 seconds, and that multiply operations consume 5 seconds of this 100 seconds total. Well, then Amdahls Law says that the enhanced execution time is going to be 5, which is the amount of time that's affected by multiplies, over 10, which is the factor of improvement, plus 95, which is the time that's unaffected, or 95.5 seconds. So although I've improved multiply operations by an order of magnitude, a factor of 10, I've only shaved off 4.5 seconds out of my total 100 seconds of execution time.